While the surface of Earth cycles through night, deep space continues its own uninterrupted sequence of physical processes. These processes are not synchronized with human activity, biological rhythms, or planetary timekeeping. They unfold according to the fundamental laws of physics, operating across distances and timescales that far exceed everyday perception. The apparent stillness of the night sky conceals an environment in constant motion, transformation, and exchange of energy. At the most basic level, deep space is permeated by radiation. Photons emitted by stars, galaxies, and diffuse cosmic sources travel continuously through the vacuum. Their motion does not slow when planets turn away from their stars or when observers sleep. This flow of radiation is a confirmed observation, measured through telescopes operating across the electromagnetic spectrum. Even in regions between galaxies, known as intergalactic space, radiation fields persist at measurable levels. One of the most pervasive features of deep space is the cosmic microwave background. This faint radiation fills the universe uniformly and represents the cooled remnant of the early universe. Its existence is a confirmed observation, first detected in the mid-20th century and measured in detail by multiple space missions. The radiation does not change appreciably over human timescales, but it continues to stream through space, passing through planets, spacecraft, and observers alike without interruption. Alongside radiation, particles also move through deep space. High-energy charged particles known as cosmic rays originate from a variety of astrophysical sources, including supernova remnants and active galactic nuclei. Their detection on Earth and in space is a confirmed observation supported by decades of measurements. These particles travel at near-light speeds, deflected by magnetic fields, but rarely stopped entirely. Their arrival at Earth continues day and night, independent of local conditions. Deep space is structured by gravity. Every massive object exerts a gravitational influence that extends indefinitely, diminishing with distance but never vanishing. As a result, stars orbit within galaxies, galaxies interact within clusters, and clusters trace the large-scale structure of the universe. These motions are confirmed through direct observation of velocities and positions over time. Even when imperceptible moment to moment, gravitational interactions continue without pause. Within galaxies, stars orbit their galactic centers along paths determined by gravitational balance. These orbits unfold over millions to hundreds of millions of years. Although the change in position over a single night is negligible, the motion is continuous and measurable across longer intervals. This is a confirmed observation derived from astrometric surveys and Doppler measurements. Stars themselves are not static objects. In their interiors, nuclear fusion reactions convert lighter elements into heavier ones, releasing energy. This process is a well-supported theory, validated by observations of stellar spectra, luminosities, and neutrino emissions. Fusion proceeds continuously in stable stars, regardless of external illumination or observation. While the rate of fusion changes over stellar lifetimes, it does not cease during planetary nights. In regions where stars are forming, molecular clouds undergo slow gravitational contraction. These clouds consist primarily of hydrogen molecules mixed with dust. Observations using radio and infrared telescopes confirm that such clouds are dynamic, with internal motions driven by turbulence, gravity, and magnetic fields. Star formation within these clouds is ongoing, with individual collapses occurring over hundreds of thousands of years. Elsewhere, stars reach the ends of their lives. Massive stars exhaust their nuclear fuel and collapse, sometimes resulting in supernova explosions. These events are rare on human timescales, but occur regularly across the observable universe. Supernovae are confirmed observations detected in distant galaxies through sudden increases in brightness. While the visible flash is brief, the physical processes unfold over extended periods before and after the explosion. The remnants of these explosions continue to expand through space, driving shock waves into surrounding material. These shock fronts heat gas, accelerate particles, and trigger chemical reactions. The existence and behavior of supernova remnants are confirmed through multi-wavelength observations. Their expansion continues long after the initial explosion, independent of observation. Black holes also participate in the ongoing activity of deep space. Contrary to some popular depictions, black holes are not constant consumers of matter. Many are quiescent for long periods. However, when material does fall toward them, it forms an accretion disk that heats and emits radiation. The physics of accretion is a well-supported theory, tested through observations of X-ray and radio emissions from black hole systems. On larger scales, galaxies collide and merge. These interactions are slow, unfolding over hundreds of millions of years, but they are confirmed observations seen in various stages across the universe. During mergers, stars rarely collide directly due to vast separations, but gravitational forces reshape galactic structures and can trigger bursts of star formation. These processes continue regardless of any local frame of reference. Between galaxies, diffuse gas traces filamentary structures shaped by gravity. This cosmic web has been mapped through observations of galaxy distributions and absorption features in distant spectra. The existence of this structure is a confirmed observation supported by simulations and surveys. Gas continues to flow along these filaments, feeding galaxies and clusters over cosmological timescales. Space is also the setting for continual electromagnetic interactions. Magnetic fields thread galaxies and interstellar space, guiding charged particles and influencing gas dynamics. These fields are detected indirectly through their effects on radiation polarization and particle motion. While their origins are still an area of active research, their presence and influence are well established. On the smallest scales accessible to observation, quantum processes continue in deep space. Atoms absorb and emit photons, ions recombine with electrons, and molecules form and break apart. These processes are confirmed through spectral observations of interstellar and intergalactic gas. They proceed according to known physical laws, unaffected by macroscopic cycles such as planetary rotation. Time itself unfolds differently in different regions of space. According to the theory of general relativity, the passage of time depends on gravitational potential and relative motion. This effect has been confirmed experimentally, though its magnitude in deep space is usually small. Nonetheless, time dilation occurs continuously, subtly shaping the evolution of systems across the universe. Despite this constant activity, much of deep space appears empty. This emptiness is real in terms of particle density, but it does not imply inactivity. Even in the most rarefied regions, radiation passes through, gravitational forces act, and quantum fields exist. The vacuum of space is not a true void, but a medium governed by well-tested physical principles. Some aspects of deep space remain open scientific questions. The nature of dark matter, inferred from gravitational effects but not directly detected, continues to be investigated. Its influence on galactic and cosmic structure is a well-supported theory, but its composition remains unknown. Similarly, dark energy, inferred from the accelerated expansion of the universe, is an open question in fundamental physics. What is certain is that deep space does not rest. While human observers experience cycles of activity and sleep, the universe operates continuously. Processes initiated billions of years ago continue, and processes whose effects will only become apparent billions of years from now are already underway. The night sky is not a pause in cosmic activity, but a momentary alignment of perspective. The apparent stillness of deep space is a consequence of scale. Changes occur too slowly or too distantly to register within a single human lifetime, let alone a single night. Yet when viewed through the lens of physics and observation, space is revealed as a system in constant motion, governed by laws that operate without interruption. Understanding what happens in deep space during periods of human rest is therefore not about identifying special events tied to nightfall. It is about recognizing continuity. The universe does not distinguish between waking and sleeping observers. Its processes proceed according to energy gradients, forces, and probabilities, indifferent to local cycles. This continuity places human experience within a broader context. The same physical laws that govern daily life also govern the fusion in stars, the motion of galaxies, and the evolution of the universe itself. While observers sleep, the universe continues its long trajectory, carrying forward processes that began long before Earth formed and that will persist long after current observers are gone. Beyond the steady background activity of radiation and gravity, deep space is the setting for continuous change, driven by motion at every scale. Nothing in the universe is truly stationary. Even objects that appear fixed against the night sky are moving along trajectories shaped by forces accumulated over billions of years. These motions are not synchronized with planetary rotation or biological cycles. They proceed continuously, governed by inertia and gravitational interaction. Earth itself moves through space at several distinct velocities. It rotates on its axis, orbits the Sun, and follows the Sun's path around the center of the galaxy. The galaxy in turn moves relative to nearby galaxies and the cosmic expansion. All of these motions are confirmed observations measured through precise astrometric and spectroscopic techniques. While they are imperceptible during a single night, they define the frame within which all local observations occur. As Earth travels, it passes through regions of interplanetary and interstellar material. The solar system is embedded in a tenuous cloud of gas and dust known as the local interstellar medium. The properties of this medium are directly measured through spacecraft observations and absorption features in stellar spectra. Interaction between the solar wind and interstellar material creates a complex boundary region at the edge of the heliosphere. This interaction continues constantly, independent of terrestrial timekeeping. Within the solar system, planets and smaller bodies follow predictable paths, yet their motion is not perfectly regular. Gravitational interactions cause small variations in orbits, leading to long-term changes known as perturbations. These effects are confirmed through precise orbital measurements and are described accurately by celestial mechanics. Over long periods, they can alter orbital shapes and orientations, even though no noticeable change occurs over a single night. Asteroids and comets also traverse the solar system. Some follow stable orbits, while others are gradually altered by gravitational encounters. These bodies continue moving whether they are illuminated or not. Their presence and trajectories are confirmed through repeated observations. Occasional collisions, while rare, do occur somewhere in the solar system on timescales ranging from years to millions of years. Beyond planetary systems, stars drift within their host galaxies. Their velocities relative to one another are measured through Doppler shifts and proper motion studies. Over time, these motions lead to changes in stellar neighborhoods, with stars passing near one another and occasionally exchanging energy. These encounters are well supported by theoretical models and observational evidence, though direct observation of individual close encounters is rare due to the vast distances involved. Galaxies themselves are not isolated. They interact gravitationally with the neighboring galaxies and clusters. These interactions produce tidal distortions, streams of stars, and gradual mergers. Such features are observed in many galaxies and provide direct evidence of ongoing dynamical evolution. These processes unfold over hundreds of millions to billions of years, continuing regardless of any observer's state of awareness. At the largest scales, the universe is expanding. Distant galaxies recede from one another, with velocities proportional to their separation. This expansion is a confirmed observation based on redshift measurements and distance indicators. It does not imply that galaxies are moving through space in a conventional sense, but that space itself is stretching. This expansion continues uniformly in all directions, unaffected by local conditions. The expansion of the universe influences deep space, even in regions devoid of matter. The distance between widely separated points increases over time, subtly altering the propagation of light and the timing of events. These effects are small on human timescales, but significant over cosmic history. They are well supported by observations of distant supernovae and the cosmic microwave background. Motion in deep space also occurs at microscopic scales. Gas clouds exhibit internal turbulence, with eddies and flows driven by gravity, magnetic fields, and energy input from stars. These motions are confirmed through spectral line broadening and spatial mapping of gas velocities. Turbulence influences star formation by regulating how clouds fragment and collapse. Magnetic fields introduce additional complexity. Charged particles spiral along magnetic field lines, creating currents and waves. These processes are observed in interstellar and interplanetary space through in situ measurements and remote sensing. Magnetic activity continues constantly, shaping plasma behavior across vast regions. Even regions considered empty experience motion at the level of quantum fields. According to well-supported physical theories, quantum fluctuations occur in the vacuum, giving rise to transient effects. While direct observation of these fluctuations in deep space is challenging, their consequences are inferred from laboratory experiments and astrophysical phenomena. Their existence represents an area where theory is well developed, but direct cosmic scale measurement remains limited. Some motions in deep space remain incompletely understood. The detailed dynamics of dark matter within galaxies, for example, are inferred from gravitational effect but not directly observed. Simulations reproduce many observed structures supporting the theory, yet questions remain about the fine-scale behavior of this unseen component. These uncertainties do not negate the evidence for motion, but they highlight the limits of current knowledge. What unites all these phenomena is continuity. There is no moment when motion ceases or resets. The universe does not pause or mark time in discrete intervals. Instead, change accumulates gradually, often invisibly, until its effects become measurable over long durations. The distinction between night and day on a single planet has no physical meaning beyond that planet's surface. The concept of sleep is biological, not cosmological. While organisms enter states of reduced activity, the surrounding universe maintains its course. The forces that drive motion in deep space are not intermittent. They act continuously, conserving momentum, redistributing energy, and shaping structure. Recognizing this uninterrupted motion alters perspective. The night sky may appear calm, but it is the projection of countless trajectories intersecting across space and time. Each point of light represents an object in motion, bound by gravity or carried by expansion. Each dark region contains fields and particles in subtle activity. The realization that deep space never rests is grounded in confirmed observation and well-supported physical theory. Where uncertainties remain, they concern the details of composition or interaction, not the presence of motion itself. Though the universe is dynamic by necessity, its evolution driven by the same principles at all times. As observers rest, the cosmos continues its long progression. Stars age, orbits evolve, and structures shift. These changes do not accelerate or slow in response to local cycles. They unfold according to scales far larger than individual experience, reminding us that human rhythms occupy only a narrow slice of cosmic time. While motion governs the structure of deep space, transformation governs its content. Matter in the universe is continuously changing state, composition, and organization. These changes are not dramatic on human time scales, but they are constant and cumulative. While observers sleep, atoms combine, stars evolve, and the chemical complexity of the cosmos slowly increases, guided by physical laws that have operated since the earliest moments after the universe began. A fundamental process unfolding throughout deep space is nucleosynthesis. In the cores of stars, lighter atomic nuclei fuse into heavier ones, releasing energy. Hydrogen is converted into helium, helium into carbon and oxygen, and in more massive stars, fusion proceeds toward heavier elements. This process is a well-supported theory confirmed by stellar spectra, energy output, and the measured abundance of elements in the universe. Fusion does not pause. As long as conditions in stellar cores remain stable, these reactions continue uninterrupted. In stars similar in mass to the Sun, fusion proceeds slowly and steadily over billions of years. In more massive stars, fusion occurs at higher temperatures and pressures, accelerating the production of heavier elements. These stars live shorter lives, but during their existence, they continuously enrich their interiors with newly formed nuclei. This internal evolution continues regardless of whether the star is observed or hidden by planetary rotation. When massive stars reach the end of their nuclear fuel, fusion ceases in their cores, leading to gravitational collapse. In some cases, this collapse triggers a supernova explosion. Supernovae are confirmed observations detected across vast cosmic distances. The explosion disperses heavy elements into surrounding space, seeding interstellar clouds with material essential for future generations of stars and planets. Although the visible explosion is brief, the chemical consequences persist for millions of years. Not all element formation occurs in stars. Some of the heaviest elements, such as gold and platinum, are produced during rare, extreme events involving compact objects. Collisions between neutron stars have been confirmed as sites of such nucleosynthesis through combined gravitational wave and electromagnetic observations. These events are infrequent, but when they occur, they dramatically alter the chemical makeup of their surroundings. The matter they eject continues to mix into the galaxy long after the initial event. Between stars, the interstellar medium serves as a reservoir of gas and dust. This medium is chemically active. Atoms collide, bond, and form molecules under conditions of low temperature and density. Observations using radio and infrared spectroscopy have identified dozens of molecular species in interstellar space, including organic compounds. The formation of these molecules is a confirmed observation, though the detailed pathways by which some complex molecules arise remain open scientific questions. Dust grains play a crucial role in this chemistry. These microscopic solid particles provide surfaces on which atoms can adhere and react. Hydrogen molecules, for example, form efficiently on dust grain surfaces rather than in free space. The importance of dust-mediated chemistry is well supported by both observational evidence and laboratory simulations. These reactions continue continuously wherever suitable conditions exist. As interstellar clouds evolve, gravity draws material inward, increasing density and altering chemical reactions. Regions within clouds become shielded from radiation, allowing more complex molecules to survive. This chemical evolution occurs gradually over hundreds of thousands to millions of years. It does not require external triggers tied to time of day or planetary position. It is driven by local conditions and persistent physical laws. In some regions, collapsing clouds give rise to protostars surrounded by disks of gas and dust. Within these disks, temperature and pressure gradients drive further chemical differentiation. Observations of protoplanetary disks reveal a rich chemistry, including water vapor, carbon monoxide, and more complex organic molecules. These observations are confirmed through high-resolution spectroscopy and imaging. Disk chemistry evolves continuously as material accretes, mixes, and cools. Even in environments hostile to complex chemistry, transformation persists. In the hot plasma near energetic objects, atoms are ionized and recombine, emitting characteristic radiation. These processes are well understood and confirmed through spectral analysis. They provide diagnostic tools for studying distant environments, but they also represent ongoing physical change independent of observation. On larger scales, galaxies themselves undergo chemical evolution. Each generation of stars forms from material enriched by previous generations. As a result, the average abundance of heavy elements increases over time. This trend is a confirmed observation, inferred from stellar populations of different ages. While the rate of enrichment varies between galaxies, the overall pattern reflects continuous chemical transformation. The intergalactic medium, though extremely tenuous, is not chemically inert. It contains hydrogen, helium, and trace amounts of heavier elements. These elements were introduced through outflows from galaxies and energetic events. Absorption studies of distant light sources confirm their presence. Chemical reactions in this environment are slow, but ionization and recombination processes still occur, driven by background radiation fields. Radiation itself contributes to transformation. Ultraviolet and high-energy photons break molecular bonds, ionize atoms, and initiate chemical reactions. This interaction between radiation and matter is a confirmed physical process observed throughout astrophysical environments. Even in regions far from stars, diffuse background radiation influences chemical states. Some transformations remain poorly understood. The exact pathways leading to the formation of certain complex organic molecules in space are still under investigation. Laboratory experiments replicate some conditions, but not all observed molecules can yet be explained fully. These gaps represent open scientific questions rather than evidence of inactivity. Importantly, transformation in deep space is cumulative. Individual reactions may be rare or slow, but over immense timescales, their effects accumulate. The elements composing planets, life, and observers themselves were forged through these continuous processes. Their origin is not tied to discrete moments, but to sustained activity across cosmic history. The idea that the universe is chemically evolving while observers rest challenges everyday intuition. On Earth, change is often associated with activity and motion. In deep space, change can occur in near stillness, mediated by sparse collisions and faint radiation. Yet the outcome is no less real. These transformations also highlight the connection between deep space and familiar matter. The atoms in living organisms were once part of stars, clouds, and interstellar dust. Their journey involved countless chemical and nuclear transformations that proceeded without interruption. Sleep, wakefulness, and daily cycles are irrelevant at this scale. The universe does not require observation to continue its chemical evolution. Reactions occur because conditions allow them, not because they are witnessed. This principle underlies all of physics and chemistry and is confirmed by consistent observation across contexts. While much has been learned about these processes, uncertainty remains in details, rates, and pathways. Ongoing observation and experimentations continue to refine understanding. Yet the central fact is clear and well supported. Deep space is chemically active at all times. As observers sleep, the universe continues to change its composition, atom by atom and star by star. These changes may not register over hours, but they define the long arc of cosmic history. Deep space is not merely a container for matter. It is an environment where transformation is constant, patient, and universal. Energy flows through deep space in forms that are largely invisible to unaided senses. Yet these flows shape the structure and evolution of the universe. While observers sleep, energy is continuously emitted, transferred, absorbed, and redistributed across cosmic distances. This activity does not require dense matter or dramatic events. It proceeds even in the most rarefied regions, governed by physical laws that apply everywhere and at all times. One of the most persistent carriers of energy in deep space is electromagnetic radiation. Stars emit energy across a broad range of wavelengths as a consequence of their internal temperatures and physical states. This emission is a confirmed observation, measured through spectroscopy and photometry. The energy radiated by stars continues uninterrupted, constrained only by the conditions within stellar interiors. Planetary rotation or local darkness does not alter this emission. Beyond starlight, diffuse radiation permeates the universe. The cosmic microwave background represents a uniform energy field left over from the early universe. Its temperature and spectrum have been measured with high precision and are remarkably consistent in all directions. While its energy density is low, it fills all of space and interacts weakly with matter, contributing to the overall energy balance of the cosmos. High-energy radiation also traverses deep space. X-rays and gamma rays originate from energetic environments such as accretion disks, stellar remnants, and galactic centers. These photons travel vast distances until absorbed or scattered. Their detection is a confirmed observation relying on space-based instruments that operate continuously. The sources that produce this radiation do so as a consequence of extreme physical conditions, not in response to observation. Energy is also carried by particles. Cosmic rays transport kinetic energy through space, interacting occasionally with atoms and magnetic fields. Their presence is confirmed through direct detection and secondary effects observed in planetary atmospheres. These particles contribute to the energetic environment of space, even in regions far from stars. Magnetic and electric fields store and transmit energy as well. In plasmas, which constitute much of the observable matter in the universe, fields and particles are tightly coupled. Energy can be transferred between them through waves and instabilities. These processes are well supported by plasma physics theory and confirmed through observations in interstellar space and near astrophysical objects. Shock waves represent another mode of energy transport. When fast-moving material encounters slower gas, energy is converted into heat, radiation, and particle acceleration. Such shocks are observed in supernova remnants, stellar winds, and galaxy clusters. While the initial event may be sudden, the dissipation of energy continues over long periods, shaping surrounding environments. On the largest scales, gravitational energy plays a dominant role. As matter falls into gravitational wells, potential energy is converted into kinetic and thermal energy. This process occurs in forming stars, galaxies, and clusters. Observations of hot gas in clusters confirm that gravitational collapse is a major source of energy input. This conversion continues as long as structures grow and interact. Gravitational interactions also redistribute energy without direct contact. Through tidal forces and orbital exchanges, energy can be transferred between objects. These processes are confirmed through the study of binary systems and interacting galaxies. Over long time scales, they alter orbits and internal structures even though no immediate change is apparent. The expansion of the universe affects energy distribution as well. As space expands, the wavelengths of photons stretch, reducing their energy. This redshifting of radiation is a confirmed observation and a fundamental consequence of cosmological expansion. It represents a gradual, continuous change in the energy content of radiation fields across the universe. Thermal energy persists even in cold regions. Gas at temperatures only a few degrees above absolute zero still contains kinetic energy. This energy is measured through spectral line widths and emission properties. While minimal by everyday standards, it is sufficient to drive slow motions and reactions over long time scales. Some energy processes remain incompletely understood. The mechanisms by which energy is transferred between scales in turbulent astrophysical plasmas are still under investigation. While observations and simulations provide strong constraints, the detailed pathways of dissipation remain an open scientific question. This uncertainty reflects complexity, not inactivity. Importantly, energy flow in deep space is directional but not purposeful. Energy moves from higher to lower density, from concentrated sources to diffuse surroundings. This tendency is described by thermodynamics and confirmed across contexts. It does not pause or reset with local cycles. Entropy increases continuously, even if the change is imperceptible over short intervals. The persistence of energy flow explains why deep space is never truly static. Even in regions devoid of stars, energy passes through in the form of radiation, fields, and particles. These flows maintain the conditions under which matter evolves and structures persist. While observers sleep, the energy budget of the universe shifts by tiny amounts. Stars lose mass through radiations, gas cools or heats, and particles exchange energy through rare interactions. Individually, these changes are negligible on human timescales. Collectively, they drive the long-term evolution of cosmic structures. Understanding these energy processes places human experience within a broader physical context. Day and night are local phenomena. Energy flow in the universe is not segmented by such divisions. It is continuous, governed by principles that operate uniformly across space and time. The fact that deep space remains energetically active at all times is a confirmed conclusion of modern physics and astronomy. Where uncertainties remain, they concern the details of interaction, not the existence of energy flow itself. As rest occurs on one planet, energy continues its passage through the cosmos. Light travels, particles move, fields fluctuate, and structures slowly change. These processes define the universe as an evolving system, indifferent to observation yet accessible through careful measurement. The night sky, seen from the surface of a rotating world, conceals this activity behind apparent stillness. In reality, energy never sleeps. It moves, transforms, and dissipates continuously, shaping a universe in constant, if often imperceptible, motion. Beyond energy flow and chemical transformation, deep space is defined by a continuous exchange of information. In physics, information is not an abstract concept, but a measurable property encoded in radiation, particle states, and gravitational influence. While observers sleep, signals cross the universe, carrying records of events that occurred minutes, years, or billions of years ago. This exchange proceeds without interruption, linking distant regions through causality rather than proximity. Light is the primary carrier of information in deep space. Every photon encodes details about its source, including temperature, composition, motion, and magnetic environment. This encoding is a confirmed observation, demonstrated through spectroscopy and polarization measurements. As photons travel, they preserve this information unless altered by interaction. The night sky is therefore a historical record, with each arriving photon representing a past state of the universe. Because light travels at a finite speed, observation is always retrospective. When radiation reaches Earth from distant objects, it reflects conditions as they were when the light was emitted. This principle is not theoretical. It is a direct consequence of special relativity and is confirmed by observation. While observers sleep, new photons continue to arrive, extending the observable record of cosmic history. Some information arrives in forms other than light. Neutrinos, nearly massless particles produced in nuclear reactions, and energetic astrophysical events stream through space with minimal interaction. Their detection is a confirmed observation, achieved using large underground and underwater detectors. Neutrinos carry information from regions opaque to light, such as stellar cores, and continue to pass through Earth regardless of human activity. Gravitational waves represent another channel of information exchange. These ripples in space-time are generated by accelerating massive objects, such as merging black holes or neutron stars. Their existence is a well-supported prediction of general relativity and has been confirmed through direct detection. Once produced, gravitational waves propagate outward at the speed of light, carrying information about their source across the universe. These signals do not pause or diminish based on local conditions. A gravitational wave generated in a distant galaxy passes through planets, stars, and observers without regard to rotation or illumination. Its passage is fleeting but measurable, and it represents a direct transmission of information through space-time itself. Information exchange also occurs through slower means. The distribution of matter in the universe encodes information about past interactions. The shapes of galaxies, the arrangement of clusters, and the filamentary structure of the cosmic web all reflect the cumulative effects of gravity over time. These patterns are confirmed observations derived from large-scale surveys. While they evolve slowly, they continue to change as structures interact. On smaller scales, the internal states of atoms and molecules encode information about their environments. Spectral lines shift in response to temperature, density, and motion. These shifts are well understood and confirmed through laboratory and astrophysical measurements. As atoms emit or absorb radiation, they transmit information about local conditions to distant observers. The propagation of information is constrained by physical limits. No signal can travel faster than light in a vacuum. This limit is a confirmed principle supported by extensive experimental evidence. As a result, deep space contains regions that are causally disconnected from one another at any given moment. Events occurring beyond a certain distance have not yet had time to influence local conditions. This causal structure gives rise to horizons. The observable universe is bounded by the distance light has traveled since the universe became transparent. Beyond this boundary, information exists but has not reached observers. This concept is well supported by cosmological theory and observation. While the universe may extend beyond the observable region, its distant parts remain informationally inaccessible for now. Despite these limits, information density in deep space is immense. Every cubic region contains overlapping signals from countless sources. Untangling these signals requires sophisticated instruments and analysis, but their presence is undeniable. The universe is continuously broadcasting its state through multiple channels. Some information is lost or transformed. As radiation interacts with matter, it can be absorbed, scattered, or re-emitted, altering its informational content. Entropy increases and fine-grained details become irrecoverable. This process is a confirmed consequence of thermodynamics and applies universally. While observers sleep, information is both transmitted and degraded across the cosmos. There are open questions about the ultimate fate of information. In the context of black holes, the question of whether information is destroyed or preserved has been a subject of long-standing debate. While theoretical progress has been made, a complete resolution remains an open scientific question. This uncertainty reflects the limits of current understanding rather than a lack of underlying physical process. Importantly, information flow does not require awareness. Signals propagate whether or not they are detected. The universe is not waiting to be observed in order to communicate its state. Observation merely intercepts a fraction of an ongoing exchange. This perspective reframes the night sky as an active interface rather than a static view. Each moment brings new information, even if it appears unchanged to casual observation. While human senses are limited, instruments reveal continuous variation in incoming signals. The steady arrival of information also links the present to the distant past. Light reaching Earth tonight may have left its source before complex life existed on this planet. Neutrinos may originate from processes occurring deep within stars at this very moment. Gravitational waves may carry the imprint of cataclysmic events that occurred long ago, only now becoming detectable. Deep space, therefore, functions as a vast communication medium. It does not transmit messages with intent, but it preserves causal connections across distance and time. This property is grounded in confirmed physical laws and extensive observation. While observers sleep, the universe continues to inform itself. Signals propagate, interactions encode outcomes, and the record of cosmic history grows longer. These processes are continuous and impartial, independent of local rhythms. Understanding this uninterrupted exchange highlights the contrast between human perception and cosmic reality. Night suggests stillness, but deep space is filled with traveling signals. Silence and darkness are artifacts of sensory limitation, not indicators of inactivity. The universe does not mark time in days or nights, it measures it in light travel distances, orbital periods, and decay rates. Information moves accordingly, shaping what can be known and when. As sleep occurs on one world, deep space remains communicative, transmitting the ongoing state of the cosmos through light, particles, and space-time itself. This exchange is constant, fundamental, and inseparable from the universe's structure. In addition to motion, energy, and information, deep space is defined by continuous structural change. The large-scale architecture of the universe is not fixed. It evolves slowly but persistently, shaped by gravity acting on matter and energy over immense spans of time. While observers sleep, this structure continues to grow, stretch, and reorganize, guided by processes that began shortly after the universe's origin. The most prominent feature of the cosmic structure is the network of galaxies, known as the cosmic web. Galaxies are not distributed randomly. They trace filaments of matter that surround vast, relatively empty regions called voids. This pattern is a confirmed observation revealed through extensive galaxy surveys and statistical analysis. The cosmic web reflects the amplification of tiny density fluctuations present in the early universe. Gravity is the primary driver of this amplification. Regions slightly denser than their surroundings exert stronger gravitational pull, attracting more matter and growing over time. This process is well supported by theory and reproduced accurately in numerical simulations. Observations show strong agreement between simulated large-scale structure and the distribution of galaxies in the real universe. Dark matter plays a central role in this process. Although it does not emit or absorb light, its gravitational influence shapes the formation of galaxies and clusters. The existence of dark matter is a well-supported theory inferred from multiple independent observations, including galaxy rotation curves, gravitational lensing, and cosmic microwave background measurements. While its exact nature remains unknown, its effect on structure formation is well established. As matter flows along filaments, galaxies form and evolve within dense nodes of the web. These environments are dynamic. Galaxies accrete gas, interact with neighbors, and occasionally merge. Each interaction alters galactic structure, redistributing stars, gas, and dark matter. These changes are observed in galaxies at various stages of interaction, providing direct evidence of ongoing evolution. Galaxy clusters represent the largest gravitationally bound structures in the universe. They contain hundreds to thousands of galaxies, along with hot gas and dark matter. clusters continue to grow by accreting smaller groups and individual galaxies. This growth is a confirmed observation, inferred from cluster dynamics and the distribution of matter around them. Within clusters, the intracluster medium undergoes continuous change. Gas is heated by gravitational collapse and by energetic processes within galaxies. It emits X-rays that are detected by space-based observatories. This emission persists continuously, reflecting ongoing energy exchange. Cooling, mixing, and shock processes operate simultaneously, shaping the thermal structure of clusters. Void regions are not static either. Although they contain little matter, they expand as surrounding structures grow denser. This expansion is a consequence of the universe's overall expansion combined with gravitational dynamics. Observations confirm that voids increase in size over time, contributing to the evolving geometry of the cosmic web. On even larger scales, the expansion of space influences structure formation. While gravity draws matter together locally, cosmic expansion stretches distances globally. The balance between these effects determines whether structures grow, remain stable, or disperse. This interplay is a central topic in cosmology and is supported by observational evidence across a wide range of scales. Some aspects of structural evolution remain uncertain. The precise way in which small-scale structures respond to dark energy, the component driving accelerated expansion, is still under investigation. Dark energy is inferred from observations of distant supernova and large-scale structure, but its physical nature is an open scientific question. Its influence, however, is clearly measurable at cosmological scales. Structural change also occurs within galaxies. Spiral arms form and dissipate, bars grow and weaken, and star-forming regions migrate. These processes are observed in nearby galaxies and supported by theoretical models. While the changes are slow, they are continuous, reshaping galactic appearance over millions of years. Even individual stars experience structural evolution. As fusion alters their internal composition, their size and luminosity change. These transformations are confirmed through observations of stellar populations at different evolutionary stages. The process is gradual but relentless, proceeding whether or not the star is visible from any particular location. The cumulative effect of these changes is an evolving universe. Structure does not emerge fully formed and remain unchanged. It develops, adapts, and sometimes dissolves. This dynamic character is a confirmed conclusion of modern cosmology, supported by observations spanning vast distances and times. The night sky presents a snapshot of this evolution. Each observed structure represents a moment in an ongoing process. While human observers may rest, the configuration of matter continues to shift imperceptibly. Over short intervals, the change is negligible. Over cosmic timescales, it is transformative. Recognizing the universe as structurally active challenges the perception of deep space as immutable. The apparent permanence of constellations and galaxies is an artifact of scale, and the forces that reshape them operate slowly, but they never cease. As sleep occurs on Earth, matter continues to flow along filaments, galaxies continue to interact, and clusters continue to assemble. These processes are governed by gravity and expansion, not by local cycles. They represent the long-term evolution of the cosmos itself. The study of this evolution relies on confirmed observations, well-supported theories, and careful distinction between what is known and what remains uncertain. While many details are still being refined, the fundamental fact of ongoing structural change is clear. Deep space, therefore, is not merely a stage on which events occurred in the distant past. It is an active system, continuously reshaping itself. The universe grows older, more structured, and more complex with time, even during the quietest hours of a single planet's night. Alongside the evolution of large-scale structure, Deep space is characterized by continuous interactions between extreme environments. Some of the most active regions in the universe are compact and localized, yet their influence can extend far beyond their immediate surroundings. While observers sleep, these environments persist in reshaping nearby matter and radiating energy into space, governed by physics that pushes conditions to their limits. One such environment surrounds compact stellar remnants. White dwarfs, neutron stars, and black holes are the endpoints of stellar evolution for many stars. Their existence is a confirmed observation supported by extensive astrophysical evidence. Though small in size, their densities and gravitational fields are extreme, creating conditions unlike those found elsewhere in the universe. Neutron stars, for example, pack more mass than the Sun into a sphere only tens of kilometers across. Their intense gravity and rapid rotation generate strong magnetic fields and energetic emissions. Pulsars, a class of rotating neutron stars, emit beams of radiation that sweep across space like cosmic lighthouses. Their regular pulses are confirmed observations, measured with extraordinary precision. These emissions continue uninterrupted, providing stable signals that can be tracked over decades. The energy output of neutron stars is not solely rotational. Some experience sudden changes in rotation rate or magnetic configuration, releasing energy in brief but intense episodes. These events are observed as bursts of high-energy radiation. While the underlying mechanisms are well supported by theory, details of how internal stresses build and release remain areas of active research. Black holes represent an even more extreme environment. Their defining feature, the event horizon, marks a boundary beyond which information cannot escape. This concept is a direct consequence of general relativity and is supported by indirect observations of black hole behavior. Outside the event horizon, matter can orbit, accrete, and emit radiation. These processes continue as long as material is available. Accretion disks around black holes are sites of intense energy conversion. Gravitational potential energy is transformed into heat and radiation as matter spirals inward. This emission is a confirmed observation across a wide range of wavelengths. Variability in brightness reflects changes in accretion rate and disk structure, offering insight into conditions close to the black hole. Some black holes produce powerful jets that extend far beyond their host galaxies. These jets consist of highly collimated streams of particles moving at relativistic speeds. Their existence is confirmed through radio and X-ray observations. The mechanisms that launch and maintain these jets involve strong magnetic fields and rotation, but their detailed physics remains an open scientific question. Interactions between extreme objects also shape deep space. Binary systems containing compact objects can exchange matter, altering the evolution of both components. These interactions are confirmed observations, detected through changes in brightness and spectral signatures. In some cases, they culminate in mergers that release vast amounts of energy. Mergers between neutron stars or between a neutron star and a black hole generate gravitational waves and electromagnetic signals. These events have been observed directly, providing a new window into extreme physics. While rare on human timescales, they occur regularly across the universe and contribute to chemical enrichment and energy redistribution. Even in the absence of dramatic events, extreme environments influence their surroundings continuously. Radiation from compact objects ionizes nearby gas, altering its temperature and chemistry. These effects are observed in nebulae and accretion regions, demonstrating ongoing interaction between small-scale extremes and larger environments. On slightly larger scales, massive stars create extreme conditions through their radiation and winds. These stars emit intense ultraviolet light and drive powerful outflows of gas. Their influence extends across surrounding regions, shaping star-forming environments. Observations confirm that stellar feedback regulates the formation of subsequent generations of stars, though the balance between suppression and stimulation remains an active area of research. Extreme environments also exist in galaxy centers, where dense concentrations of stars and gas interact. Tidal forces, collisions, and energetic processes combine to create dynamic regions. These centers evolve continuously, influenced by both local interactions and large-scale structure. The persistence of extreme conditions in deep space challenges assumptions about equilibrium. Many regions operate far from thermal or dynamical balance, maintained by continuous energy input. These states are not temporary anomalies. They can persist for millions or billions of years. This persistence is supported by observations of long-lived active regions. Despite their intensity, extreme environments occupy a small fraction of cosmic volume. Most of space is relatively calm by comparison. Yet the influence of extremes is disproportionate. Through radiation, jets, and gravitational waves, they affect regions far beyond their immediate location. Some aspects of extreme physics remain uncertain. The behavior of matter at nuclear densities, the nature of singularities, and the unification of gravity with quantum mechanics are unresolved questions. These uncertainties represent frontiers of knowledge rather than gaps in observation of activity. What is clear is that deep space hosts environments where physical laws operate at their limits. These environments do not switch on and off with local cycles. Their activity is continuous, driven by intrinsic properties and long-term evolution. As observers sleep, pulsars continue to pulse, accretion disks continue to glow, and jets continue to stream outward. These processes unfold on timescales and energy scales far removed from daily experience. The presence of extreme environments underscores the diversity of conditions in the universe. Deep space is not uniform or tranquil everywhere. It contains regions of intense activity embedded within vast expanses of relative calm. Understanding these environments requires careful observation and theory, with clear distinctions between confirmed phenomena and open questions. While many details remain under study, the ongoing nature of extreme processes is firmly established. Deep space, therefore, is not only active in subtle ways, it also hosts some of the most energetic and persistent phenomena known. These extremes continue to shape the cosmos, indifferent to planetary nights, contributing to an ever-evolving universe. In parallel with extreme environments and large-scale structure, deep space is governed by cycles that operate far beyond biological or planetary rhythms. These cycles involve the birth, evolution, and eventual dispersal of matter, repeating across the universe with variations set by mass, environment, and time. While observers sleep, these cycles continue without pause, defining the long-term behavior of cosmic systems. One of the most fundamental cycles is the life cycle of stars. Stars form from collapsing clouds of gas and dust, evolve through stages determined by their mass, and ultimately return material to space. This framework is a well-supported theory confirmed by observations of stellar populations at different evolutionary stages. At any given moment, stars across the universe occupy every phase of this cycle simultaneously. Star formation itself is an ongoing process. Molecular clouds fragment and collapse under gravity, forming dense cores that heat and ignite nuclear fusion. Observations using infrared and radio telescopes confirm that new stars are forming continuously in many regions of the universe. These processes are not synchronized. They begin and end according to local conditions rather than global timing. As stars age, they alter their surroundings. Stellar winds and radiation gradually remove gas from their vicinity, influencing subsequent star formation. These feedback processes are confirmed observations visible in star-forming regions and clusters. They demonstrate that stellar evolution is not isolated, but coupled to the broader environment. When stars reach the end of their lives, they return material to space through gentle outflows or explosive events. Planetary nebulae and supernova remnants mark these transitions. Their structures are directly observed and reveal the redistribution of enriched material into the interstellar medium. This recycled matter becomes the raw material for future stars, completing the cycle. Galaxies participate in similar cycles. Gas flows into galaxies from surrounding space, fuels star formation, and is later expelled through winds or energetic events. Observations of inflows and outflows confirm this exchange. While the balance between accretion and loss varies among galaxies, the cycling of matter is a persistent feature of galactic evolution. On even larger scales, clusters of galaxies exchange matter and energy with their surroundings. Gas falls into clusters, heats, and may later be redistributed through interactions. These processes are observed through X-ray emission and gravitational studies. They operate continuously, reshaping cluster environments over billions of years. Cosmic cycles also include the transformation of radiation. Light emitted by stars is absorbed by dust and re-emitted at longer wavelengths. This energy redistribution is confirmed through observations across the electromagnetic spectrum. Dust grains heat and cool, participating in a cycle of absorption and emission that persists wherever dust exists. Chemical cycles extend across these scales. Elements forged in stars are dispersed, incorporated into new systems, and transformed again. This process is confirmed by observed abundance patterns and isotopic ratios. The chemical evolution of the universe is therefore cyclical rather than linear, though each cycle introduces gradual change. Even the expansion of the universe participates in a form of cycle, stretching space and cooling radiation fields. While expansion itself is not cyclical in the strict sense, it interacts with matter and energy in repetitive ways, influencing structure, formation, and radiation over time. The details of how expansion will shape the distant future remain an open scientific question. What distinguishes these cosmic cycles is their independence from short-term events. They are driven by gravity, thermodynamics, and nuclear physics, not by external scheduling. Their continuity is confirmed by observing systems at different stages across space, effectively sampling different moments in the same processes. These cycles also operate across overlapping timescales. Star formation may take millions of years, while chemical enrichment unfolds over billions. Radiation transport occurs at the speed of light, while structural evolution is far slower. All of these processes coexist, contributing to a layered temporal structure. Human concepts of rest and activity have no direct analog in these cycles. There is no universal pause between stages. Matter transitions smoothly from one state to another, guided by probabilities and constraints rather than discrete steps. Some aspects of these cycles remain uncertain. The efficiency of star formation under different conditions, the ultimate fate of expelled gas, and the long-term balance of matter and energy are active areas of research. These uncertainties reflect complexity, not inactivity. The existence of continuous cosmic cycles underscores the persistence of change in deep space. While individual events may be rare or brief, the cycles themselves ensure ongoing activity. At any given moment, somewhere in the universe, a star is forming, another is dying, and matter is being recycled. As observers sleep, these cycles proceed without awareness of observation. The universe does not wait or reset. It evolves through repeated processes that shape its composition and structure. Recognizing these cycles places human time into context. A single night encompasses an infinitesimal fraction of stellar or galactic evolution, yet those processes continue seamlessly through it. The apparent stillness of the night sky belies the layered, cyclical activity unfolding beyond perception. Deep space, therefore, is not only dynamic in motion and energy, but rhythmic in transformation. Its rhythms are slow, vast, and overlapping, are governed by fundamental laws rather than local experience. These enduring cycles connect the present universe to its past and future. They ensure continuity, diversity, and change across cosmic time. While sleep occurs on one world, the universe continues its cycles, indifferent to rest yet foundational to existence. Beyond cycles of matter and energy, deep space is defined by continuous interaction with time itself. Physical processes do not simply unfold within time, they shape how time is experienced, measured, and distributed across the universe. While observers sleep, time progresses unevenly across different regions of space, influenced by motion, gravity, and expansion. This behavior is not philosophical abstraction, it is a confirmed consequence of modern physics. According to the theory of relativity, time is not universal. Clocks in different gravitational fields or moving at different velocities tick at different rates. This effect, known as time dilation, has been confirmed experimentally through precision measurements on Earth and in orbit. In deep space, where gravitational fields and velocities vary widely, time passes at different rates in different locations, continuously and without synchronization. Near massive objects such as neutron stars or black holes, gravitational time dilation becomes significant. Clocks closer to these objects run more slowly relative to distant observers. While direct placement of clocks near black holes is not possible, the effects of strong gravity on emitted radiation are observed through gravitational redshift. These observations confirm the underlying theory and demonstrate that time itself is affected by extreme environments. Motion also alters the passage of time. Objects moving at high velocities experience time more slowly relative to stationary observers. This effect is small at everyday speeds but becomes measurable at relativistic velocities. In astrophysical jets and rapidly orbiting systems, relativistic motion influences observed timing and emission patterns. These influences are confirmed through precise measurements of periodic signals. The expansion of the universe introduces another temporal dimension. As space expands, the rate at which distant events can influence one another changes. Light emitted in the past travels through an expanding medium, stretching its wavelength and altering its timing. This effect is observed in the redshift of distant galaxies and is a fundamental feature of cosmology. Because of finite light speed and expansion, the universe contains a layered temporal structure. Different regions are observed at different stages of cosmic history. While observers sleep, new regions cross into observational reach as light continues its journey. This gradual unveiling is a confirmed consequence of light travel time rather than any change in intrinsic activity. Time also governs decay processes in deep space. Radioactive isotopes formed in stars and supernova decay at characteristic rates. These decay processes are well understood and confirmed through laboratory and astrophysical observations. They proceed continuously independent of external conditions, providing natural clocks that record the passage of time. Some isotopes decay over millions or billions of years, influencing the thermal and chemical evolution of planets and star-forming regions. Others decay rapidly, contributing transient energy. In all cases, decay continues steadily, marking time in a way that does not pause for observation or rest. Time influences the evolution of orbits as well. Gravitational interactions gradually alter orbital parameters through mechanisms such as tidal dissipation and radiation emission. These effects are confirmed in binary star systems and planetary satellites. Over long periods, they lead to orbital decay or stabilization, reflecting the slow action of time on motion. Even empty space is subject to temporal change. Vacuum energy associated with dark energy appears to drive accelerated expansion. While its physical nature remains an open scientific question, its influence on the universe's expansion rate is confirmed through observation. This acceleration alters the long-term future of cosmic structure, changing how time will shape the universe. The arrow of time in deep space is defined by increasing entropy. Energy spreads, gradients diminish, and systems evolve toward equilibrium. This principle is confirmed across physical systems and emphasized universally. While local decreases in entropy occur, the overall trend persists. Time's direction is therefore embedded in physical processes. Despite this, some aspects of time remain mysterious. The origin of time's arrow, the nature of time before the early universe became transparent, and the ultimate fate of temporal structure are open scientific questions. These uncertainties coexist with a strong understanding of how time behaves under known conditions. Importantly, time in deep space does not align with biological or planetary rhythms. Sleep and wakefulness have no meaning beyond specific organisms. The universe does not recognize cycles of rest. Time flows according to geometry and motion, not experience. While observers sleep, clocks throughout the universe continue to tick, each at its own rate. Stars age, orbits evolve, and radiation propagates. These processes define a continuous temporal fabric that does not pause or reset. Recognizing time as an active dimension reshapes the understanding of deep space. It is not merely a backdrop for events, but a variable influenced by mass, energy, and motion. This influence is confirmed by observation and central to modern physics. The night sky presents an illusion of simultaneity. In reality, each observed object occupies a different moment in time. While sleep occurs on Earth, distant regions experience their own temporal conditions, shaped by local physics. Deep space, therefore, hosts not only continuous activity, but continuous temporal differentiation. Time flows everywhere, but not identically. This diversity of temporal experience is a fundamental property of the universe. As rest occurs on one planet, time advances across the cosmos, carrying systems forward along paths set by physical law. These paths are uninterrupted, indifferent to observation, and essential to the universe's ongoing evolution. Deep space is also shaped by continuous processes of loss. Matter and energy do not merely circulate and transform. They are also steadily removed from systems through mechanisms that thin, erode, and disperse structure over time. These processes are subtle on short timescales, yet they are fundamental to the long-term evolution of the universe. While observers sleep, stars lose mass, systems shed energy, and ordered structures gradually weaken. One of the most pervasive forms of loss in deep space is radiative emission. Any object with a temperature above absolute zero emits radiation. This principle is confirmed by fundamental physics and extensive observation. Stars, planets, dust clouds, and even diffuse gas continually lose energy by emitting photons. This emission proceeds continuously, independent of external conditions or observation. For stars, radiative loss is central to their existence. The energy produced by nuclear fusion in stellar cores is balanced by the energy radiated from their surfaces. This balance determines stellar structure and lifetime. Radiation leaves the star at the speed of light, carrying energy into surrounding space. Over billions of years, this loss gradually reduces stellar mass, a process confirmed through observation and theory. Even after nuclear fusion ceases, stellar remnants continue to lose energy. White dwarfs cool by radiating their residual heat. Neutron stars emit thermal radiation and in some cases lose rotational energy through electromagnetic emission. These cooling processes are confirmed observations, measured through changes in luminosity and temperature over time. They continue steadily, marking the gradual fading of once active systems. Loss also occurs through particle outflows. Many stars produce winds that carry mass away from their surfaces. These winds are directly observed through spectral features and interactions with surrounding material. While individual particles are few, the cumulative effect over time can significantly alter a star's mass and environment. This process operates continuously even in otherwise quiet stellar systems. At larger scales, galaxies lose matter through outflows driven by stellar activity and central energetic sources. Gas can be expelled from galaxies into intergalactic space, reducing the material available for future star formation. Observations confirm the presence of such outflows in many galaxies. Their long-term impact on galactic evolution is an active area of research, but the existence of mass loss is well established. Gravitational systems also lose energy through radiation of a different kind. Accelerating masses emit gravitational waves, carrying energy away from the system. This effect is predicted by general relativity and has been confirmed through direct detection. In compact binary systems, the loss of energy through gravitational radiation causes orbits to shrink over time, eventually leading to mergers. This gradual loss proceeds continuously until a final event occurs. Energy loss contributes to the aging of cosmic structures. Orbits decay, rotations slow, and dynamic systems settle into lower energy configurations. These trends are observed across scales, from planetary systems to galaxies. They reflect the tendency of systems to move towards states of reduced available energy. Loss is also evident in the dispersal of material. Molecular clouds that give rise to stars are eventually disrupted by radiation, winds, and explosions. Their dense structure dissipates, returning gas to more diffuse states. This dispersal is a confirmed observation in star-forming regions. It represents a form of structural loss that balances the creation of new stars. Even the largest structures are subject to gradual erosion. Galaxy clusters lose energy through radiation emitted by hot gas. Over very long timescales, this cooling can alter cluster dynamics. While clusters remain bound, their internal states evolve as energy is lost. These processes are observed through X-ray emission and temperature measurements. At the scale of the universe, expansion contributes to effective loss. As space expands, radiation loses energy through redshift. This energy is not transferred elsewhere in a recoverable form. The process is a confirmed observation and a fundamental aspect of cosmology. It represents a gradual dilution of energy density over time. Entropy plays a central role in these losses. As energy spreads and becomes more uniformly distributed, it becomes less available to do work. This increase in entropy is a confirmed principle of thermodynamics. It applies universally, governing the direction of physical processes. While local decreases in entropy occur, the global trend persists. Loss does not imply disappearance. Matter and energy are conserved in total, but they become more diffuse, less concentrated, and harder to organize into complex structures. This distinction is crucial. Deep space is not emptying, it is changing its distribution of resources. Some losses remain poorly constrained. The ultimate fate of energy in an expanding universe, particularly in relation to dark energy, is not fully understood. These uncertainties represent open scientific questions rather than contradictions of observed loss processes. The cumulative effect of continuous loss shapes the universe's future. Stars exhaust fuel, structures relax, and energy gradients diminish. These changes occur slowly, imperceptible over a single night, yet relentless over cosmic time. While observers sleep, photons leave stars, particles drift outward, and waves carry energy away from dynamic systems. Each act of loss is small, but together they define the aging of the universe. Understanding loss provides balance to the picture of continuous activity. Creation, transformation, and interaction are accompanied by dissipation. This balance is fundamental to physical law. The night sky, viewed from a single moment, conceals this steady thinning. Objects appear unchanged, but they are subtly different than they were moments before. Energy has left them, matter has shifted, and time has advanced. Deep space therefore embodies not only motion and creation, but also decline in the physical sense. Systems evolve not toward stasis, but toward lower energy states, guided by thermodynamics. This decline does not signal an end in any immediate sense. It is a long-term tendency, unfolding over durations far beyond individual awareness. Yet it is always underway. As sleep occurs on Earth, loss proceeds across the cosmos. Stars dim fractionally, orbits adjust, and radiation escapes into expanding space. These processes define the quiet, persistent erosion that accompanies all cosmic activity. Despite continuous loss and dissipation, deep space is not trending uniformly toward uniformity. Rather, counteracting processes persist, driven by instability, fluctuation, and amplification. While observers sleep, the universe continues to generate structure out of apparent disorder. This coexistence of decay and emergence is one of the most important and least intuitive facts about cosmic behavior. Instability is a central mechanism through which structure arises. In many physical systems, small disturbances grow rather than fade. This principle applies throughout astrophysics. Slight density differences in gas clouds can amplify under gravity, leading to collapse and structure formation. This process is a well-supported theory and is confirmed by observations of star-forming regions at different stages of collapse. Thermal instability also operates in deep space. Gas that cools slightly faster than its surroundings can lose pressure support, becoming denser and cooling even more rapidly. This runaway process leads to the formation of cold clouds within hotter environments. Such multi-phase structures are confirmed observations in interstellar and intergalactic gas. They illustrate how order can arise locally even as energy is lost globally. Magnetic instabilities play a similar role. Magnetic fields store energy that can be released suddenly or redistributed through waves and reconnection events. These processes are observed in space plasmas, including stellar environments and diffuse gas. While the detailed physics of magnetic reconnection remains an active research area, its occurrence is well established and contributes to ongoing restructuring. Turbulence, often associated with disorder, can also promote structure. Turbulent flows create density variations that seed collapse and chemical differentiation. Observations of molecular clouds show complex filamentary patterns shaped by turbulence. These patterns are not static, they evolve continuously, driven by the interplay of motion, gravity, and energy dissipation. At galactic scales, instabilities in rotating disks can generate spiral arms and bars. These features arise from collective gravitational effects and persist for long periods. Their existence is a confirmed observation supported by theoretical models. Spiral structure may strengthen, weaken, or shift over time, reflecting ongoing dynamical evolution. Even in the expanding universe, structure formation continues. Although expansion tends to separate matter, gravity counteracts this effect locally. The result is a universe in which dense regions grow denser, while voids expand. This dual behavior is confirmed by large-scale surveys and simulations. It demonstrates that expansion does not erase structure uniformly. Fluctuations in radiation fields also contribute to structure. Variations in radiation intensity influence heating, ionization, and chemistry. These effects are observed in regions near energetic sources and across cosmic environments. Radiation-driven instabilities can alter gas dynamics, creating new patterns and boundaries. At the smallest scales, quantum fluctuations provide seeds for macroscopic structure. In the early universe, tiny fluctuations in density were amplified by expansion and gravity, eventually giving rise to galaxies and clusters. This origin of structure is a well-supported theory, strongly constrained by observations of the cosmic microwave background and large-scale structure. Importantly, the generation of structure does not violate thermodynamics. While local order increases, it is accompanied by greater disorder elsewhere. Energy is dissipated, entropy increases globally, and structure emerges as part of that process. This balance is confirmed by physical theory and observed behavior across systems. The persistence of structure formation means that deep space is never settling into complete uniformity. Even as some systems fade, others are born. The universe exhibits a dynamic equilibrium in which creation and decay coexist. Some questions remain unresolved. The detailed role of dark matter properties in shaping small-scale structure is still under investigation. Similarly, the influence of dark energy on future structure formation is an open scientific question. These uncertainties affect predictions of long-term evolution, but do not negate the observed presence of ongoing structure. The interplay between instability and dissipation operates continuously. There is no preferred moment when structure formation is active and loss is inactive. Both processes occur simultaneously, governed by local conditions. While observers sleep, new density contrasts emerge, instabilities grow, and matter reorganizes. These changes are imperceptible on short timescales, but fundamental over long ones. They ensure that the universe remains complex rather than homogeneous. This persistence challenges the notion that the universe is winding down uniformly. Instead, it reveals a system capable of sustaining structure far longer than naive intuition might suggest. The night sky reflects this persistence through its enduring patterns, even as those patterns slowly evolve. Deep space, therefore, is not only a site of gradual fading, it is also a place where new forms arise from subtle imbalances. This duality is a confirmed and essential feature of cosmic evolution. Understanding this balance clarifies why the universe remains richly structured despite immense age and expansion. The same laws that permit dissipation also permit emergence. Neither dominates absolutely. As sleep occurs on Earth, the universe continues to organize itself in pockets and patterns, even as energy spreads and structures age. This simultaneous creation and erosion defines deep space as an active, evolving system rather than a static endpoint. At the deepest level, what continues in deep space while observers sleep is not a collection of isolated events, but the uninterrupted operation of physical law itself. The universe does not require activity in the everyday sense to remain active. Its fundamental rules govern how matter, energy, space, and time behave at every moment, ensuring continuity across all scales. This persistence is the most comprehensive and least visible process of all. Physical laws do not switch on or off. Gravity continues to curve space-time, quantum fields continue to fluctuate, and particles continue to interact according to fixed probabilities. These principles are confirmed through experiment and observation across environments ranging from laboratories to distant galaxies. Their consistency is one of the strongest empirical findings in all of science. In deep space, quantum processes occur continuously. Virtual particles arise and vanish within allowed limits. Fields maintain baseline energies, and probabilities govern interactions. While individual quantum events are unpredictable, their statistical behavior is well understood and confirmed by theory and experiment. These processes do not depend on density, temperature, or awareness. They occur even in near-perfect vacuum. At slightly larger scales, atomic transitions continue. Atoms absorb and emit radiation according to discrete energy levels. These transitions are observed throughout the universe via spectral lines. Even in extremely diffuse gas, atoms undergo transitions over long time scales. Each event represents the operation of quantum electrodynamics, proceeding without interruption. Fundamental constants remain constant. Measurements of physical processes across billions of years show no confirmed variation in quantities such as the speed of light, the charge of the electron, or the strength of fundamental forces. This stability is a confirmed observation within current measurement limits. It ensures that processes occurring now are governed by the same rules as those that occurred early in cosmic history. Causality continues to operate. Events influence other events only within the limits imposed by space-time structure. Signals propagate, interactions occur, and consequences unfold according to deterministic or probabilistic laws. This causal framework is confirmed across physics and underpins all prediction. While observers sleep, causes continue to generate effects, even if they are not immediately observed. The universe also continues to explore its possible states. Within the constraints of physical law, systems evolve along paths determined by initial conditions and interactions. This exploration is not goal-directed. It is the natural outcome of dynamics. Stars follow evolutionary tracks, galaxies interact, and radiation propagates because the laws permit and require these outcomes. Importantly, there is no universal frame in which the universe is at rest. Every reference frame is local, and motion is always relative. This principle is a confirmed result of relativity. As a consequence, there is no global moment of inactivity. Somewhere, processes are always underway relative to any observer. Even the concept of deep space is relative. What is empty on one scale is structured on another. What is quiet in one wavelength is active in another. This layered activity is confirmed by multi-wavelengths observation and theoretical understanding. It reflects the fact that physical law operates uniformly, but its manifestations depend on scale and context. Some foundational questions remain open: why physical laws have the form they do, why constants take their observed values, and whether deeper unifying principles exist are unresolved. These are active areas of theoretical research. Their uncertainty does not undermine the observed continuity of law. It highlights the boundary between what is known and what remains to be understood. The future evolution of the universe will continue to be governed by these same laws. Whether expansion continues indefinitely, structures eventually fade, or new phases emerge depends on parameters still under study. What is certain is that whatever occurs will do so continuously, not in discrete pauses. From the perspective of daily life, sleep marks a suspension of awareness. From the perspective of the universe, there is no corresponding suspension. Processes do not acknowledge observers. They do not wait, slow, or accelerate in response to attention or absence. The night sky then is not a scene of rest, but a cross-section through ongoing lawfulness. Every point represents matter and energy obeying rules that never sleep. The apparent stillness arises from the mismatch between human timescales and cosmic ones. Understanding what happens in deep space while observers sleep ultimately reveals something fundamental. The universe is not event-driven in the way human experience is. It is rule-driven. Events emerge from the continuous application of those rules, not from episodic activation. This perspective dissolves the boundary between night and day at the cosmic level. There is no nocturnal universe and diurnal universe. There is only a universe in constant operation, structured by unbroken regularity. While observers rest, physical law continues to operate everywhere. Stars continue to shine, particles continue to interact, space-time continues to curve and expand. These processes are not coordinated with sleep, nor do they require awareness to proceed. The continuity of physical law is the deepest answer to what happens in deep space during periods of rest. It is not that specific events occur because it is night, but that nothing stops occurring because it is night. Deep space remains active because it cannot be otherwise. The universe is defined by ongoing processes, governed by immutable rules. Awareness may pause, but reality does not. In this sense, sleep reveals not a pause in the cosmos, but the contrast between human rhythms and a universe that never disengages from its own laws. Deep space continues, uninterrupted, carrying forward the same processes that shaped the past and will define the future.